Well, welcome everybody to today's talk. Thanks to all of you for coming. Harsha Pereira is a candidate for our open lecturer position, and this talk is part of his interview today. Harsha got his PhD in our department in 2015, working with Tim Swartz, and has published extensively in the well-known area of cricket analytics. At this point, it's probably safe to say that Harsha is one of the world's leading experts on cricket analytics, and in fact has been interviewed in the popular media for his expertise, so he's getting out and making use of his fame. Harsha is currently a sessional instructor with the department, where he's taught our Intro to Stat course for social sciences, our Stat 203, several times, and is on his second iteration now with Stat 100. Yeah, his second iteration with Stat 100, experiencing the joys and sorrows of the 500-seat classroom. Today, Harsh is going to give a lecture on normal distributions aimed at a Stat 100, 201, 203 kind of an audience. We'll have a 30 to 40-minute talk, and then there will be time for questions at the end, and those questions can either be questions from the perspective of a student or questions about the teaching of the course. Welcome, Harsha.
So many new faces today in my class. Maybe I'm in the wrong class, I'm not sure. Anyway, so I'm in my full suit today because I had some interviews in the morning. So I thought of coming with the new suit just for a change today. So anyway, so we'll start the lecture today. So today I'm going to discuss about normal distributions, and I already gave a little bit kind of a introduction last week in my last class. So in this chapter, actually, we are going to cover, so these are the topics you need to make sure that you know in this class. What is a normal distribution? And the empirical rule 68, 95, 99.7 rule. And then we are going to discuss about the standard normal distribution. And then we are going to calculate or find some normal probabilities. And in order to do that, we are going to use the standard normal table, and then we are going to do some kind of a special calculation finding a value given a probability. So I am not sure whether I can cover the last part, but I will try my best to cover the first 4 topics in this lecture. Sorry. In last class, I started discussing about density curves, and I gave you a brief idea about what is a density curve. So this is kind of an example before I am starting the normal distribution here today. So here is a histogram of vocabulary scores of 947 7th graders. So this is in your textbook. So this will show you the histogram, and then on top of the histogram they draw the density curve. So what is a density curve? Actually, I already explained that last class. The smooth curve drawn over the histogram is a mathematical model for this distribution, and this curve is a density curve. So the special feature of a density curve is the total area under the density curve is 1, or if you take it as a percentage, it is 100%. So we are going to use this feature throughout this lecture because we are going to calculate some probabilities using normal distribution. This normal distribution is a special density curve. So now we'll move to the normal distribution. So one particularly important class of density curves are the normal curves. So specifically, it is a special density curve. So the normal curves describe the normal distribution. So we discussed about the shape of distributions in 2 weeks ago, like skewed distributions and symmetric distributions. So normal distribution is a symmetric distribution. So normal curves are symmetric, single peaked, and bell shaped. So that's a regular thing for the normal curve. So it is a symmetric, single peak, and bell shape. Any specific normal curve is described by giving its mean mu and standard deviation sigma. We have already discussed about what is mean and what is standard deviation in the distribution. So depending on the mean mu and standard deviation sigma, you are getting a different normal distribution. So the standard deviation sigma is directly corresponding to the width of the distribution. So higher the standard deviation, wider the distribution is, and the mean mu is the center value, so it gives you an idea about the average of the center value of the distribution. So again, any specific normal curve is described by giving its mean mu and standard deviation sigma. So if you have any questions, feel free to ask me, because I am happy to explain that again if you want to ask any questions. So now we are going to discuss about this empirical rule, which is 68, 95, 99.7 rule. So what is it saying? Say your distribution is approximately normal. It is saying, say your mean is mu and standard deviation is sigma, then approximately 68% of the observations fall within one standard deviation of mu. So that means this blue color area. So mean middle is mu, this is mu plus sigma, mu plus 2 sigma and mu plus 3 sigma to right, mu minus sigma, mu minus 2 sigma and mu minus 3 sigma to left. So the empirical rule is saying approximately 68% of the observations are fallen within one standard deviation of the mean. That means in between mu minus sigma and mu plus sigma. So this blue color area. And then approximately 95% of the data or the observations fall within two standard deviation of mean. That means 95% of the data are in between mu minus 2 sigma and mu plus 2 sigma. And 99.7% of the observations fall within 3 standard deviation of mean. That means literally 99.7 of the data are in between mu minus 3 sigma and mu plus 3 sigma. So this is the 68, 95, 99.7 rule. So in this class actually we are going to use this rule at the beginning, and then we are trying to do something else using the standard normal distribution and go for those calculations. So now I will describe one example for this 68, 95, 99.7 rule. So the example is the distribution of Iowa Test of Basic Skills (ITBS) vocabulary scores for 7th grade student in Gary, Indiana is close to normal. So that's saying, it is saying the distribution is approximately normal. Suppose the distribution is no, so actually this is the standard notation just to show that this the distribution is normal. So n is stand for the normal. Within parentheses, first parameter is the mean and the second parameter is the standard deviation. So this is how we denote normal distribution random variable in statistics. So normal with mean 6.84 and standard deviation 1.55. So the first we are going to sketch the normal density curve for this distribution. So in order to do that, I will use the document reader. So you can write it at the same time. So say my x is ICBT scores and x is normally distributed with mean 6.84 and standard deviation 1.55. So now I am going to sketch the normal distribution. So when you are sketching the normal distribution, it has to be bell shape, single peak and symmetric. This is not the best one, but keep that. So my middle value is my mean value, which is 6.84, and I am going to say mu plus 1 sigma, mu plus 2 sigma and mu plus 3 sigma into the right, and mu minus sigma, mu minus 2 sigma and mu minus 3 sigma to the left. This is how we sketch the normal distribution. So my mu plus 1 sigma is 6.84 plus 1.55, which is 8.39, and my mu plus 2 sigma is 6.84 plus 2 times 1.55, which is 9.94, and my mu plus 3 sigma is 6.84 plus 3 times 1.55, so which is turn out to be 11.49. And I'm doing the same thing to the left side, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So mu minus sigma is 6.84 minus 1.55, which is 5.29, and mu minus 2 sigma is 6.84 minus 2 times 1.55, which is 3.74, and mu minus 3 sigma is 6.84 minus 3 times 1.55, which is 2.19. So this is how we sketch a normal distribution according to the description we have. So you need to make sure to show what is mu, mu plus 1 sigma, mu plus 2 sigma, and mu plus 3 sigma. To the left side, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. When I sketch in the it doesn't have to be the exact thing, but it has to be a sketch which is sensible. Okay, any questions with the sketching? Yes. Actually, y-axis is my probability, actually density. So when you are sketching this, you don't have to worry about putting any y-axis. Maybe you can just write here your x-axis as the ICBT scores, and your y-axis is actually the probability or the density. So actually, when you are sketching the thing, you don't have to worry about providing what is your y-axis. Does it make sense? Or? So because I said this is a density curve, so the area under the density curve is always representing the total probability. So the area under the density curve is the probability. So that means y-axis is literally you are providing the probability. Okay, sorry. And when you are sketching the graph, actually you don't have to worry about what is your y-axis. So basically, x-axis is your ICBT scores, and then you are representing it with mu, mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Okay. And the second question, so sketch the normal density curve for this distribution. Actually, I have that here in the slide. Actually, you can use that too. So the density curve, and then you have all the ITBS scores. The part 2 is asked what percent of ITBS vocabulary scores is between 3.74 and 9.94. So we can use the sketch we already draw here. So 3.74, sorry, 3.74 is representing mu minus 2 sigma here, and 9.94 is representing mu plus 2 sigma here. From the empirical rule, we know 95% of the observations or 95% of the data are in between 2 standard deviations. So according to the question, what percent of ITBS vocabulary scores is between 3.74 and 9.94? So the answer should be, I'm asking from the audience. Yeah, so the answer should be 95% from the empirical rule. Okay, any questions again about the answer? So I'm showing that here in the red color area in the sketch. So you can see it is in between 3.74 and 9.94. So about 95% of the scores are within 2 standard deviation of mu. And the third question is asked, what percent of the scores is below 3.74? What percent of the scores is below 3.74? Any guess or any answer? Because now we already sketched the diagram. So we all know 3.74 is mu minus 3 sigma. So the question is asking what percent of the scores is below 3.74. We know 99.7% of the data is in between 3 standard deviation. That means in between mu plus 3 sigma and mu minus 3 sigma. From the converse rule, the total probability is 100%. Therefore, the area less than 3.74 and area greater than 9.94 should be equal to 100% minus 99.7%. from the converse rule. I already discussed about converse rule in last class. First probability rule we use. Because the total area is 100%. Oh, sorry. The total area is 100%. 3.74 is mu minus 2 sigma and 9.94 is mu plus 2 sigma. So the total area in between two standard deviation is 95%. Therefore, the area less than 3.74 plus area greater than 9.94 should be 100 minus 95%. Sorry, I made the mistake before. So the total area should be 100 minus 95%. Because of the symmetry, this area which is less than 3.74 is going to be equal to the area greater than 9.94. Therefore, the percentage of ITBS vocabulary scores less than 3.74 should be 5% divided by 2, which is 2.5%. Did you get it? Or you want me to explain that? Because I made a mistake assuming that is 3 sigma. So the total area is 100% and area in between 3.74 and 9.94 is 95%. Therefore, the area less than 3.74 plus area greater than 9.94 should be 100% minus 95%, which is 5%. Therefore, the area less than 3.74 should be 5% divided by 2, which is equal to 2.5%. Any questions? Yeah, I got a this mark here. Okay, that's fine. Okay, so now we are moving to so we discussed about normal distribution. Now we are going to discuss a technique called standardizing. So we'll see what is standardizing. So as I said, any normal distribution can be described by using its mean and standard deviation. So therefore, depending on the mean and the standard deviation, you are getting a different normal distribution. Okay, so depending on the mean and the standard deviation, you are getting a different normal distribution. So what we are going to do here is standardizing means we are going to standardize all the normal distributions. So all normal distributions are the same if we measure in units of size sigma, that means size of standard deviations from the mean mu as center. So regardless of the size of the standard deviation, it can be any number, but if we can measure the distance from the mean from the units of standard deviation, that is called, we are standardizing the normal distribution. Okay. So changing these units is called standardizing. So this technique we denote as the standardizing. So that means our units are coming from how many standard deviations above or below from the mean, regardless of the size of that. So this is the standardizing formula. Say if x is an observation from a normal distribution that has mean mu and standard deviation sigma, the standardized value of x is, we denote it as a z score, is equal to, you subtract the mean and divide by standard deviation. So x is coming from a normal distribution with mean mu and standard deviation sigma. In order to standardize x, what you are doing is you subtract the mean and dividing by standard deviation sigma. So this is, we denote as a z score, and z scores are always number of standard deviations above or below above the mean. Okay. Anybody wants to explain that again? It wants me to explain that again. Okay, so we will go to some examples, then you will get the idea. For the standardizing, so the example, the heights of women aged 20 to 29 in the United States are approximately normal with mean 64.2 and standard deviation 2.8 inches. So now we are going to standardize a given height according to the distribution with mean 64.2 and standard deviation 2.8. say we want to find the Z score for a given height. What we are doing, we just take the height value, whatever the given height value, and we subtract the mean of the distribution and divide by the standard deviation 2.8. That way we can get the corresponding Z score for this given height. So, for example, say a woman 70 inches tall, for example, has standardized height. So, that means your height value is 70 now, minus 64.2 divided by 2.8. So, in that case, the Z score for a woman who is 70 inches tall is 70 minus 64.2 divided by 2.8, which is 2.07. What is this mean? 2.07. That means if you are 70 inches tall, that means you are 2.07 standard deviations above the mean of that distribution. That's what this standard score means. So, now your units are coming from how many standard deviations above or below the mean. Another example, similarly, a woman with 5 feet, that means 60 inches tall, what is her standardized height? So, that means 60 minus 64.2 divided by 2.8, which is equal to negative 1.50. So, what is this negative means? That means 1.5 standard deviations less than the mean height. So, the positive numbers are corresponding to the above the mean, and the negative numbers means less than the mean, and the units are coming from how many number of standard deviations above or below. Any questions? Okay. So, now so far we discussed about the normal distribution, and then we try to standardize the normal random variable. So, now we will see what is standard normal distribution. Okay. A standard normal distribution, so this is the formula that we use to standardize a normal variable into standard normal by subtracting mean and dividing by standard deviations, and then the units are coming from how many standard deviations above or below from the mean. Okay. So, the standard normal distribution is a normal distribution with mean 0 and standard deviation 1. So, as example, I will write it down here. So, you have a variable x which is normal with mean mu and standard deviation sigma. Then you sketch the distribution. So, middle is mu, this is mu plus sigma, this is mu plus 2 sigma, and this is mu plus 3 sigma, the regular sketch that we are doing. And this is mu minus sigma, this is mu minus 2 sigma, and this is mu minus 3 sigma. Okay. So, now we are going to convert our normal distribution into standard normal distribution by subtracting mean and dividing by standard deviations, and then that distribution is known as a standard normal with mean 0 and standard deviation 1. So, we will see how it works. So, this is my normal distribution. Okay, now we will see what happened here. So, now my x value is mu. Now, I am going to standardize my x value in order to get this standard normal variable. So, Z score is equal to x minus mu divided by standard deviation. So, now I am referring to my mu, x is equal to mu now. So, that means mu minus mu divided by sigma, that means it is equal to 0. In my normal variable, so it is mu, now it is in my standard normal, it is equal to 0. So, now we will see what happened with mu plus sigma. So, now my x is equal to mu plus sigma, and now I am going to standardize. So, again x minus mu divided by sigma, that means now my x is mu plus sigma. So mu plus sigma minus mu divided by sigma. So mu and mu get cancels out, and then sigma divided by sigma is equal to 1. So that means mu plus sigma is corresponding to plus 1 here. So likewise, if you do for mu plus 2 sigma, that is corresponding to 2 here, and mu plus 3 sigma, it is corresponding to 3 here. So you can do that by yourself. Same thing with the left side. Mu minus sigma is going to be minus 1, mu minus 2 sigma is going to be minus 2, mu minus 3 sigma is going to be minus 3, because when you standardize, all these distance are from how many standard deviations above or below the mean. So if it is mu plus sigma in the normal, in the standard normal it should be, because it is 1 standard deviations above the mean, therefore it should be plus 1 here. And for mu plus 2 sigma in the normal, it is 2 standard deviations above the mean, therefore once we standardize, it has to be 2 here, because now it is 2 standard deviations above the mean. Therefore this is my standard normal, this is normal with mean 0 and standard deviation 1. So literally you convert your normal variable with mean mu and standard deviation sigma into standard normal with mean 0 and standard deviation 1. So doing that, we can convert any normal distribution into a standard normal distribution. Therefore the units are coming from how many standard deviations above or below the mean. Okay, any questions about this? Okay. Sorry, I have to go back and forth. So the slide is showing you the representation again. So if a variable x has any normal distribution with mean mu and standard deviation sigma, then the standardized variable is z score, which is x minus mu divided by sigma, has a standard normal distribution with mean 0 and standard deviation 1, and the shape and everything is exactly same as the normal distribution. Now the units are coming from how many standard deviations above or below the from the mean. Okay, any questions? Okay. So now we know, okay, now we learn about the normal distribution, and now we convert our normal distribution into standard normal distribution. So now we are going to do some calculations to find some probabilities using this standard normal distribution. So in order to find probabilities, first we need to know a term called cumulative proportions or cumulative probability. What is a cumulative probability or cumulative proportion? So the cumulative proportion for a value x in any given distribution is the proportion of observations in the distribution that are less than or equal to x. So if your value is x, and if you want to find the cumulative probability for x, that means you need to find the area less than x, that is the cumulative proportion, because we are going to use this cumulative probability or cumulative proportion in order to calculate standard normal probabilities. So now we convert our normal variable into standard normal. That means now we have a one single distribution called standard normal distribution, which helps us to calculate the normal probabilities using a one single table called standard normal table. So because all normal distributions are the same when we standardize, that's what we did before, we can find areas under any normal curve from a single table, and this is known as a standard normal table. So in your textbook, back of the textbook, you have a table called table A, which is the standard normal table. I will show you here. So this is the standard normal table. It's on page 690. So now you can see there are two tables actually, one for the positive Z scores, one for the negative Z scores, which is going from -3.4 till 0, and then one is for the positive Z scores. We're going from 0 till 3.4. So now you know Z scores are the how many standard deviations above or below the mean, and so all these probability, these numbers on the table are the cumulative probabilities or cumulative proportion for this specific Z score. Like as example, say minus 2.60, the table value is 0.0047. What is this mean? This means probability of Z score less than minus 2.60 is 0.0047. Literally that is the cumulative proportion or cumulative probability for Z score to minus 2.600. So likewise you can read this table, because all these table values are the cumulative proportions or cumulative probabilities for that particular Z score. So this is for the positive, this is for the negative numbers, and this is for the positive numbers. Okay. Any questions? Because I am going to use this table again in a graphical way, then you have a better idea. Perfect. That's good. Okay, so the standard normal table, I showed you that, which is table A, is a table of areas under the standard normal curve. The table entry for each value Z is the area under the curve to the left of Z, or the cumulative proportion or the cumulative probability. So we'll see, okay, how we read that table. Suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.81. Okay. So now in the standard normal table, you have Z scores in the first column, and then you have the 100th decimal point. This is like 0.700, 0.71, 0.72 likewise, and these probabilities on the table are the cumulative probabilities or the cumulative proportions for this given Z score value. So we want to find the probability of Z score less than 0.81 using the table. Probability, the Z score is less than 0.81. So now first we need to go to the first column and see where 0.8 is, and then 0.81 means the second decimal point should be 1. So that means we are referring to this row and this column. So the row is for the 0.8 and the column is for the second decimal point 0.01. So that means this is the probability or the cumulative proportion, which is Z less than 0.81. So the answer should be 0.7910. So if you just sketch the diagram for the standard normal curve, so the x-axis is going from 0, 1, 2, 3 and negative 1, negative 2, negative 3. So minus 0.81 is somewhere here in this sketch. So we are looking for this green color area. So this area according to the table is 0.7910. Any questions about this calculation? So this is the very basic, and this is the first time I am explaining this. So I want to make sure everybody understand what I am saying. Okay. Anybody wants to explain? Okay. So this is how you calculate the probability Z less than 0.81. So how do we calculate the probability Z greater than 0.81? So we have to use the converse rule, because we know the total area under the curve is 100% or 1 as a probability. So now we want to calculate the probability Z greater than 0.81. That means actually this area, right? So this area is equal to 1 minus this green color area from the converse rule. Therefore, if you want to calculate any probability Z greater than any particular number, that means you have to use the converse rule, that is equal to 1 minus probability Z less than that number, because from the table you are always getting the cumulative proportion or cumulative probability. So if you want to calculate anything, probability Z greater than any number, that means it is equal to 1 minus probability Z less than that number. So Z less than that number is the number that you are getting from the table, because table is always providing you the cumulative probability or the cumulative proportion for that particular Z score. Any question? Yes. So cumulative probability is telling you like what is the probability. So as example, this I am looking for probability Z less than 0.81. So this is telling you what is the probability of getting an observation which is Z score is less than 0.81. The total probability less than 0.81. So the table is directly providing you the cumulative probability for Z less than 0.81 as 0.7910. Got it? Makes sense? Maybe I can talk to you after class. Okay. Okay, I have 2 more minutes. And what happens if you want to find the area in between two Z scores? So in this case, first one is Z less than 0.81. Then I said Z greater than 0.81 is equal to 1 minus probability Z less than 0.81. So now we are going for the third step. We are going to calculate the probability in between two Z scores. Okay. Restart required. These things always happen to me in my lectures. Okay. Sorry for that. So we see, find the proportion or the probability of observations from the standard normal distribution that are between minus 1.25 and 0.81. So now we are going to look for the probability or the proportion in between two standard scores using the standard normal table. So the problem is clear. So that case, so the probability so the area in between negative 1.25 and 0.81 is the area. Okay, so this is a sketch. So this is the area we are looking for. The area in between negative 1.25 and less than 0.81. So this red color area is the area we are looking for. So there are two ways you can calculate this probability. The first technique is you just find the area which is probability Z less than 0.81, that means this entire area, and then subtract the area probability Z less than negative 1.25. Right, this is what is shown from the sketch. So the area probability Z less than 0.81, and then you take the area probability Z less than negative 1.25, then you subtract this area from this area, that will give you this area. Make sense? From the graphical representation, the area that we are looking for. So therefore it's always important to sketch the diagram and then see which area you are looking for, because that's important. So basically in this case we are looking for this middle area, which is equal to probability Z less than 0.81 subtract the area probability Z less than negative 1.25. So from the standard normal table, probability Z less than 0.81 is equal to 0.790, which I already showed in the previous one, and the probability Z less than negative 1.25, you can directly get it from the table, because table is always providing you the cumulative probability, that is equal to 0.1056. So the answer should be 0.7910 minus 0.1056. The answer is 0.6854. Any questions about this? So first you have to sketch the diagram and then make sure the area that you are looking for, then do the math, simple math, right, some subtraction. So this is only one method of calculating this probability. There is another way. Since we know the total area is 1, so if we can subtract this area and this area from 1, then we are getting this area, because now we need this red color area. So since the total area is 1, we can subtract this area, that means probability Z less than negative 1.25 and the probability Z greater than 0.81, then you are getting the same answer. Make sense? So that's for the homework, because my lecture is done now. I have to go to department. Okay, so that's the end of the class today, and my office hours tomorrow. So if you have any questions, you can come and talk to me in my office hour, and see you next week. So I'm going to discuss about some couple of examples again. So this is we denote as the forward calculations. Then I will get to the backward calculations in my 2 hours lecture sorting next week. Okay, thank you so much.
Questions for Harsha?
You can meet me in my office hour.
Student. So I still don't get, you said that these like histogram things were probabilities, so what I don't get is, say for the test scores, how would you read off from there the probability that I get a 7 on the test?
You mean this one, right? Or maybe, I don't know. Okay, so as example, if you want, so this is the distribution for the vocabulary scores of 947 7th graders. So as example, if you want to find the probability, if you randomly select a student, his score is less than, his score is less than 6, getting a 7. So because this is a continuous distribution, so in this case, if you say what is the probability of student is getting exactly 7, according to the continuous distribution rule, it is equal to 0. So I will actually explain that to you in my office hours, like if you need more explanation for that.
Really well.
Okay. Because the continuous distribution and discrete distribution is not in our syllabus, but I can definitely explain it to you.
To Rachel's question, so and in reality there are people getting score 7, so how
so because it's a continuous distribution, there are infinity number of cases saying which is equal to exact same number. So in that case, the probability of something equal to the exact same number in this case is equal to 0. So as example, in a continuous distribution, you can find the probability something greater or equal to some number, or less or equal to some number, or greater than number, or less than number. But if it is exactly equal to something, it is equal to 0. Again, I can explain it to you in my office if you want. Yeah.
Other questions?
I was just wondering, like, will you have in a previous lecture, I guess I'm asking this as one lecturer to another, in a previous lecture will you have asked them, or will you have gone over with them why we're interested in the normal distribution?
Why we interested in the normal distribution?
Yeah, you know.
Because I discussed with them about different density curves and shape of the distributions and everything, and then normal distribution is one of the most common distributions that we are dealing with. So, and again, it is in the part of our syllabus. So then that's why actually I am just teaching about the normal. And then I told them about this is a special distribution, and most of the times we want to have our distribution, like in real life it is highly unlikely, but we always want to have our distribution as normal because it is like more mathematically easy than the other kind of distribution to deal with. So I explained them kind of the importance of normal distributions and the shape of the distributions and everything.
This lecture. Okay, thanks.
The previous lecture actually it is about calculating descriptive statistics and then describing the shape of the distributions, like if it is skewed and symmetric, and what are the center measurements and the spread measurements. So after that we are going to the normal distribution, so it's special case. Okay. Thank you.
Can you explain to me what probability density means?
What probability density means? So probability density means basically, so in this example, so this is the distribution of the vocabulary score, and say if you want to find, so you can see like most all the data is in between like 1.5 to like 12. So that means this is the density, like all the data is in between these two numbers. So if you want to find any random person's probability, like any random person saying probability less than, the vocabulary scores less than 4, that means you have to find this particular area which is directly showing you the probability for having a student score less than 4. Did you get what I mean? Or?
7. What does this?
Density at 7. That means the so as example here. So that means the actual I would say so the probability means actually in this case if it is 7, that means you have the highest kind of number of people in this particular slot. That means it has the highest probability. According to the scores, we can see like most of the people are getting scores in between 6 and 8. So that means this has the highest kind of probability area compared to the other areas. Oh, thank you. I like my office hours.
From one lecturer to another, what's your opinion on doing away with tables, like not teaching tables in our intro classes?
Instead of using table, what are the other methods I can use?
Well, getting them to compute the various quantiles, say from using software, or I've sometimes I give them a few possible values to choose from, rather than providing them with the whole table.
So you asking the question as a student or just
no, as a fellow lecturer.
Okay.
What's your opinion on
so
getting? Because in real life nobody uses tables, right? So what's your opinion?
So
on
in the class actually I'm just showing them, okay, this is how we use the table, but for sure we can use some software like R or SAS or anything, or maybe we can use graphing calculator, or maybe we can use some applets like stat track or something, and you can just plug the numbers and you can get the probabilities. But in the class I want to first let them know, okay, this is how you actually use the table. Otherwise it's a black box, they don't know, like they just plug the numbers and they are getting the numbers. So in the class I want to make sure, okay, this is how you actually do this. If you want, you can use the software, or you can use applet, or you can use graphing calculator. There are several methods you can use. I mean, in terms of the class, but in the class they have to definitely use the standard normal table for the calculations. So depending on the question, sometimes I am asking from use the empirical rule or use the standard normal table. For stat 100 actually we just use the empirical rule. Yeah. Thank you.
I had a question. Why did I want to find the probability that Z was less than 0.81? Why did I want to find the probability that Z is less than 0.81? That was the example you did.
That's a random number I took. You can use any number there. But,
what number would I want to use? Is everything 0.81? Oh.
Because I use 0.81 just to show you the example how to use the table. If you want, you can use any number. Like I can explain that using 1.28 or maybe any other number here. I just use 0.81 because it's just an example. Just to show you how to use the table.
But how does that relate to anything? The 0.81,
I mean,
where does that come from?
So this is the Z score 0.81. So we standardize our normal value. So the standardized values are always, it is number of standard deviations above or below. So in this case it is 0.81 standard deviations above the mean, and for the example, I want to find the probability z less than 0.81 from the table, because I'm just halfway done. I need to, next week I'm discussing like how you actually get the x value and then convert into z and then go to the probability. So
Okay.
today I'm kind of like halfway done. So you have to wait
So
for that.
I'm asking about tomorrow's lecture.
You're asking about tomorrow's lecture.
Tell me how to estimate the probability that less than 0.815.
0.815. So one way is actually in this class you just round it up to the second decimal point. Say if it is 0.815, then you can find just z is less than 0.81, or you can just you can just round it up, like you can just find the probability from the table. So 0.815 is in between probability of 0.81 and 0.82. So basically you can get the average of these two. But in my class actually you can just round it up to the second decimal point, because the table is only showing you up to the second decimal point, and then you can just get that as z score and then can find the probability. Sorry? Jigo.
Harsha, I want to ask you, do you feel comfortable to using the new technology, like, for example, iClicker, Top Hat,
Definitely,
in
yeah.
lectures?
So I wanted to use like next term, I guess, I don't know, either iClick or Top Hat or something, and then even in my Stat 100 classes I have some quizzes going on. Like during the class I am giving a quiz and then I have 4 answers, so then students can interact with me. So if you use like a iClicker, then you know the responses, or Top Hat, then you have like a real-time responses, then you can kind of discuss that with the student in front of the class. So definitely, yeah. So it depends on the number of students, but most of the 100, 200 level classes you have around 200 students. So I think it's a good way to interact with students using some technology. Like I think department is probably, and there are some other softwares I think the department can pay for that. Then students have the access to that, because sometimes I am reluctant to ask students to pay like additional 35 bucks for the iClicker or maybe a Top Hat or something. Maybe, I don't know, I'm just saying because I know Domi is next to me. There are some softwares like department can buy it, and then students have the access to the software. Then maybe we can use that in the entire department for whatever the courses that we are dealing with, more than 100 or 200 students. Just a suggestion.
I like your answer. It's a lot like the advertisements we're seeing right now for the BC Liberal government. Well, you know, I'll use them next semester if I'm hired. If we re-elect the BC Liberals, we'll get a tax break and get new bridges as well. It was a good answer. Harsha, thank you very much for the talk and for taking the time to interview with us today. If you want to review some of this lecture opportunity, the recording will be, you'll send me the link as soon as it's available, and the recording will be put up, and I'll send that out. And I'm talking to the people who haven't seen it yet, so that's completely useless. Let's thank Harsha once again.
And I want to tell you, thank you so much for actually having me here, because I know it's the entire department decision. So thank you so much. I really appreciate that. And I don't know, I'm just here for now 8 years. It's like my kind of alma mater, and I have something inside me for SFU, because just doing something for SFU is like something I dream for. So yeah, again, thank you so much for having me here. And I know this is not my best lecture because I'm kind of nervous and totally different way I'm teaching in front of my students, but anyway, because it's up to you to take the decision. So thank you so much again. Thank you so much. Thank you so much for coming here.